Okay, so I have started the presentation. Once again, I request you to please confirm that you can see the presentation. Hello,
Yes, sir.
you can see the presentation. Thank you. Thank you very much. So I'll just quickly revise a few ideas we discussed in the last class. So it's about the variation of a function. If you have a function that depends on only one variable, the variation of the function will be proportional. The change of the function will be proportional to the change in the step size of the independent variable, that is dx, times the slope of the function. So when you increase the number of independent variables, as in this case, you have got three independent variables, as in three spatial coordinates, then the variation of the function phi d phi will be equal to the sum of the products of the step size times the partial derivative of the function with respect to a particular coordinate. So here you have three terms, three products of partial derivative with respect to a coordinate times its step size, and then you sum up overall the step sizes. And so the next thing, by referring to the well-known concept of the vector dot product, we were able to establish that the variation of a function over three variables will look like this. Function phi depends on x, y, z, therefore d phi, the variation as in change of phi will be equal to del phi dot dl. And that is the three-dimensional upgrading of the case of a function that depends on only one variable as shown over here. So I hope all of you can understand these points clearly. I hope all of you can hear me. Oh, someone's trying to enter from the outside. No, I mean, you should always enter using the DICT ID. That's, I don't know what. Anyway, so this is known as the del operator, vector differential operator. And the vector differential operator looks like this. When we apply it on a scalar, it is simply putting the operator in front of the scalar. But if it's a vector, then you have to do it in one of two ways. Either put a dot between the operator and a vector quantity, or put a cross between the operator and a vector quantity. Remember, del is not a quantity. By itself, del doesn't mean anything. Del is an operator. Nevertheless, it also has the properties of vectors, and as such, it still has to respect certain properties of vectors. So then we talked about the divergence operation. Divergence of a vector is given by this formula we talked about. You also worked on some tutorial questions. Today I'll take up these things in greater detail. If at a particular point divergence of A is positive, you call that point a source point. If at a point the divergence of A is negative, you call that a sink. And when divergence is neither positive nor negative, and there's only one number that satisfies this condition, which is 0, then you have neither a source nor do you have a sink. Okay, then we talked about the vector cross product, and this was, this is the general cross product that you have. We applied the idea of a vector cross product, which is set down by this determinant, to the vector differential operator. Curl of A is given as this, and this is the point where we ended. So so basically this is what it is. If you see curl of A having three components, you write this determinant, this table, x cap, y cap, z cap, del del x, del del y, del del z, ax, ay, az. So that is for curl of A. And if you have divergence of A with three components, ax, ay, az, this is what you write. Del del x of ax plus del del y of ay plus del del z of az. So that is all there is to it for the divergence operation, for the curl operation. And of course, we also have the scalar multiplication. So when you have got del of a scalar, as in this, del phi, you write this, x cap del del x of phi, y cap del del y of phi, z cap del del z of phi. So these are the three things that you have to do all the time. So what are the things that we can do? We shall discuss those things in detail in the tutorials. Now let us look at certain implications of these three operators, or interpreting the physical meaning of these operators, because ultimately we shall do physics. So we may be using the language of mathematics, but we shall still, I mean, that's got a purpose to serve. And the purpose is that we have to understand nature through this language. You speak to somebody, that person doesn't speak your language, then you have to make an interpretation. So you have to understand that person says, what that person is saying. So nature is that person over here, and you have to understand what she is saying. So let us see. Here we are. There's the gradient operator. First, we looked at this formula earlier. You have a function phi that depends on three coordinates, x, y, and z. What is the change of that function phi? Infinitesimally small change, d phi. And that is equal to del phi dot dl. What is dl? dl is the step size. It is a vector, and as such, it will have two things, a magnitude and a direction. So the magnitude is given by this, vert dl, that is the step size. So let us see. You can see that this is a dot product. Del of phi is a vector. Phi is a scalar, but when you apply the del operator on phi, then the outcome is a vector quantity. And we shall have to understand the meaning of del of phi now. So del of phi is a vector quantity dot dl. So d phi is equal to magnitude of del phi. So when you have got a dot product of two vectors, what do you write? A dot B. So what do you do? Magnitude of A times magnitude of B times cosine of the angle between the two vectors A and B. It is a scale. Will give you a scalar out. Scalar magnitude of del phi. You've got the scalar magnitude of dl and cos theta. What is cos theta? Cos theta is the angle between the two vectors. What are the two vectors? dl is one vector and del of phi is the other vector. Now I have written something over here. Two phrases. One is dl is step size and theta is the direction of the step. Suppose you're standing at a point. Let us say any point, you're standing somewhere on the ground. And I ask you to take a step. You usually take roughly like 1 meter. So magnitude of dl is the magnitude of the distance that you take in your step. You can take if you're a tall person, you will take a step size of 1 meter, let's say. If you're a short person, you'll take a step size of, let's say, half a meter, or maybe 3/4 of a meter. So the step size that you're taking is the distance that you're covering in taking one step. What is theta? Theta is the direction of the step. Let's try to understand that. I ask you, you take a step of 1 meter, let's say you're satisfactorily tall. You take a step of 1 meter or half a meter, whatever, in the north direction. So with respect to your reference point, reference line, east-west, you will take a step of, let us say, if you say that 0 degree is east-west, as you have in a compass or a circle, the horizontal axis defines east-west, and 0 degrees set with respect to, let us say, the east direction. So you will say, I take a step of 90 degrees. 90 degrees with respect to the east direction is north. Or I say, no, you take a step in the east direction. So you will say that I take a step of 1 meter in the east direction. Therefore, if you take a step in the east direction, theta will be 0 degrees. So you can take a step in any direction, regardless of the value of theta. Whatever is the stride, length of the stride that you take will be the step size. That is the magnitude of your dl. And the direction of dl will be given by the angle theta. And that will give you the full information of what is the length of your stride and in what direction have you taken the stride. So when theta is equal to 0, let us now follow this thing. When theta is equal to 0, cos theta is equal to 1. That is the maximum value you can get for cos theta. I hope you have not forgotten your school knowledge of trigonometry. Cos theta varies between a maximum value of 1 plus 1 to a minimum value of minus 1. That is the variation of cos theta. So the maximum value of plus 1 you can take. So if you take, let's see. So when you say theta is equal to 0, what do I mean by theta is equal to 0? Meaning that these two vectors, gradient of phi, del of phi is a vector. Phi is a scalar, but as soon as you apply the del operator on phi, you get a vector. Del of phi and dl are two vectors. If they're aligned in the same direction, then theta is equal to 0. But if they're aligned in the same direction, then basically it means that you are taking a step. Your step size is dl. You're taking the step in the direction of del phi. That is what it means. You are the one who you have full control on the direction on which you can take your step, and as well as but the direction is phi is maximum in the direction of phi. You can immediately see that if cos theta has got the maximum value of 1, it means that when dl and del phi are aligned in the same direction, d phi will give you the maximum change. If incidentally cos theta is equal to 90 degrees, then you'll have no change at all, 0. D phi will be equal to 0, cos 90 degree will be 0. So d phi changes, phi changes maximally in the direction of del phi, with dl being fixed. Dl, as I said, dl is a step size. So you say, I'm fixing the length of the stride that I'm taking to 1 meter. I'm more interested in the direction. So basically, what it now turns out to be is that if your step size, if you're going along the gradient of phi, this is the vector. If you're going along the del of phi direction, then you'll get the maximum change in phi. So what is del of phi? Del of phi gives the rate of change with respect to space in the direction of the maximum change. So now notice something. Del of phi is actually is a vector quantity. Therefore, it has got both a magnitude and a direction. So del of phi will give you 2 points of information. First of all, it will tell you how much phi is changing with respect to the spatial coordinates. Do not forget, del of phi is a derivative, except that suppose I give you a function. Function depends only on one coordinate, fx, let us say. What is the rate at which f is changing with respect to x? You will say df dx. Okay. But now instead of f depending on only one coordinate, I say you have got a function that depends on 3 coordinates, x, y, z. Then I say that what is the rate at which this function phi is changing. Don't say d phi dx or d phi dy, d phi dz, because it's not just with respect to one coordinate. The function is changing with respect to all 3 coordinates. Therefore, the most general answer that you should be giving me is that the function, the rate at which this function is changing with respect to the spatial coordinates is del phi. So that is what del phi, the magnitude of del phi, gives the rate of change with respect to space. And this thing is, del of phi is also conveying rate of change with respect to space is all right, but it is also telling you in the direction of the maximum change. Because d phi is maximum when dl is directed along del phi. So that is what it is. Let us look at certain other feature, the extremal condition. What is the extremal condition? Let us try to understand that. Suppose I give you a function that depends on x. Again, let us think of our one-dimensional analogy. It's not a very difficult thing to think of. The function is changing as x is changing. X changing, the function is also changing. So what is the condition for, the function can, at one point of time, the function can reach its peak value and then come down, or reach its minimum value and go up. So what is this, the condition where for the extremity, where the function reaches its greatest value or the least value, whatever it is? You're talking about the extremal condition. So in one dimension, or with respect to one Cartesian coordinate, let's say, well, it can be other coordinates also, but for the time being, let us keep ourselves confined to the Cartesian coordinate system. You will say that if it is for one dimension, you write df dx is equal to 0. Right. That can be either a maximum or a minimum. To distinguish between the maximum and the minimum, you shall have to look at the second derivative. Right. And so here also, incidentally, for the second derivative, for a minimum that is a stable point, the second derivative is positive, and for a maximum that is the unstable point, the second derivative is negative. Okay, anyway, so you have the extremal condition, gradient of phi in 3 dimensions. It's not just df dx is equal to 0, it is del of phi is equal to 0. And what is del of phi? It's a gradient. So x cap del phi del x plus y cap del phi del y plus z cap del phi del z. You can see that this is a vector quantity with 3 components. Each component has the magnitude, which is the partial derivative of the function with respect to its particular coordinate, times the unit vector along that coordinate. And all these 3 things will add up to being equal to 0. Now, in the last tutorial, we discussed a problem where we talked about a constant vector. P, vector P has got 3 components, and I said that if the vector P is a constant quantity, then all the 3 components are also constants. But now we are looking at something more specialized than that. Here we are talking about a vector which has got 3 components, and the 3 components are adding up to 0. What is your conclusion from this formula? Your conclusion is that since the direction of x cap, y cap, and z cap are mutually perpendicular, as I've written over here, it implies that independently del phi del x, del phi del y, and del phi del z are equal to 0. Why are they 0? Individually, why they should be 0? Suppose I give you 2 terms. Here we have got 3 terms. Let us say I have given you 2 terms. And I'm saying that the 2 terms are adding up to 0. You will be wondering whether, I mean, the sum can be 0 in 2 different kinds of ways. What? That individually each term can be equal to 0. Or the terms are cancelling one another out, and therefore you have equal to 0. Is the former case true over here, or latter case true over here? Here we have got 3 terms, and all of them are adding up to give you vector 0. Does it mean then that individually they are each equal to 0? Each of them is equal to 0? Or is it that they are cancelling one another out to give you 0? Well, the answer is the first one. Why so? Because they are mutually perpendicular. So whatever is happening along the x direction can't affect anything along the y direction. For cancellation, let's say 2 trains are traveling in opposite directions, but along the same axis. Then there's something like a cancellation, or if they're traveling in the same direction, there's something like a reinforcement, whatever. But here 2 trains are traveling in mutually perpendicular tracks, or 2 things are happening in 2 different tracks, mutually perpendicular. So whatever happens along one direction can't affect anything in the other direction. So when 2 things are perpendicular to each other, they can't cancel each other out. And so it is that these 3 things are perpendicular to one another, and they cannot cancel one another out. Therefore, the 3 directions are being mutually perpendicular, meaning, and they're all adding up to 0. These conditions mean that individually they are equal to 0. Del phi del x, del phi del y, and del phi del z are all equal to 0. And that is how it should be. Because if you think of the one-dimensional example, f depends only on x. In that case, extremal condition is df dx is equal to 0. But now you have an extremal condition where f depends on 3 coordinates, x, y, and z. What is the extremal condition, therefore? Del phi del x is equal to 0, del phi del y is equal to 0, del phi del z is equal to 0. Incidentally, recall the solution of the last question of the last tutorial, T1. There was a question that was tutorial 1. There was a question that was given to you, h as a function of x and y. How did you find the extremal condition? Del h, del x is equal to 0, del h, del y is equal to 0. Okay. So that is the interpretation of the gradient operator. Two things we have concluded from the gradient operator. First, the gradient operator applied on a scalar function gives the maximum rate of change in the direction along which the maximum changes, gives the rate of change in the direction along which the maximum change is happening. That's the first conclusion as given here in this box. And the second condition is that when you have an extremity of the function, then individually all the three partial derivatives will be equal to 0. Like I said, like the gradient operator, we also have to now, because today we shall be interpreting the physical import of all these differential operators, vector differential operators. We have discussed the physical interpretation of the del operator. So the del operator applies in three ways. Once applied on a scalar, you have the gradient operation, which we have just discussed. Then applied on a vector, there are two ways. One is the divergence operation and the other is the curl operation. So let us now look at the understanding of the divergence operation. Here we are. So here's a situation whereby I have given you a vector. It's just a simple example for you to understand the meaning of the divergence operation. A vector G is equal to minus y x cap divided by square root of x squared plus y squared plus x square root of x squared plus y squared into y cap. I'm asking you to find the magnitude of this vector. How do you find the magnitude of a vector? Take the dot product of the vector with itself. That is to say, in this case, you'll have to take G dotted with itself, G dot G. Take the dot product of the vector with itself, and then you find the square root of the dot product. Well, let us see what is the magnitude of this thing. When you take the dot product of this vector with itself, x cap dotted with itself will give you minus y square root of x squared plus y squared into minus y square root of x squared plus y squared. And then similarly, you'll have the second term dotted with itself, x divided by the square root of x squared plus y squared dotted with x divided by the square root of x squared plus y squared. But that is what it is. Okay, now let us see what this thing comes to. In the denominator, you've got two square roots of the same thing. Basically, then it means x squared plus y squared. And so it is here also. And you have x squared plus y squared. So x squared plus y squared is a common term in the denominator of these two products. So you have got x squared plus y squared in the denominator. In the numerator, what have you got? Minus y into minus y is y squared. X into x is x squared. X squared plus x squared divided by x squared plus y squared is equal to 1. So basically, the magnitude of this vector g squared is equal to 1. When you take the square root of this thing, it will give you 1 anyway. So basically, the unit vector is not changing at all. And yet the vector is changing its direction. Let us see. I shall discuss this thing in greater detail in a supplementary set of notes very soon. So let us try to see. What you have got over here is actually a circle vector. A circle. This. You've got y, you've got x, it's got a magnitude of 1, and I'm showing that the arrow is going in the anti-clockwise direction. If it had gone this way, then that would have been clockwise, but here we are going in the anti-clockwise direction. How can we say that we are going in the anti-clockwise direction? Just look at the vector itself. The equation of the horizontal line is y is equal to 0, and the equation of the vertical line is x is equal to 0. So y is equal to 0 and x is equal to 0. So let us just put y is equal to 0. When we put y is equal to 0, this whole thing will vanish. 0 divided by square root of x squared plus 0 squared. So 0 by x vanish. And here y will vanish, and you'll just have x divided by square root of x squared, which is 1. I'm sorry, x. So x divided by square root of x squared, which is x. So x divided by x will be 1. So g will be equal to y cap when y is equal to 0. First term will vanish and the second term will just be y cap. So g will be equal to y cap. Y cap points in the upward direction. Right. So it will be going that way. Now, at this point, x is equal to 0. If x is equal to 0, then let's see. The second term will vanish. X equal to 0 divided by 0 squared plus y squared. So x 0 divided by y, 0. And the first term will be minus y divided by square root of y squared, which is y. So minus y divided by y will be minus x cap, minus x cap. So at this point where x is equal to 0, your equation, the vector is pointing in the negative x direction. X cap would have gone to the right, but minus x cap is going in the left. So at this point, you're pointing this way. At this point, you're pointing upwards. So basically, immediately you can see that it's just going round and round in circle. You can put all the other quantities and check for yourselves. So there is no big issue with that. Anyway, so that's the answer to the question. How do we know the direction? That is to say, the arrows. So now I'm asking you to find the divergence of this operator. You should be able to make an educated guess that the divergence of this vector will be 0. Let's see how. Del of G. Del of G is what? Del x of the x component of G, which is this, plus del y of the y component of G, which is this. So that is what you have. Del x of the x component of G minus y by x squared plus y squared square rooted over plus del y of the y component of G plus del z of the z component of G, but G doesn't have any z component, therefore it is equal to 0. Okay, now let us take the derivative. When we are taking a partial derivative with respect to x, y is to be treated as a constant quantity, so minus y goes out of this bracket as a constant should, and so you'll have to take del x of 1 upon square root of x squared plus y squared square rooted over, so that should be minus half. So this is x squared plus y squared raised to minus half. So minus half into x squared plus y squared raised to minus 3 halves. Then you go inside the square root. You have got to take we are just applying chain rule over here actually. So you have to take 2x. So you have to take the derivative of x squared will be 2x. So 2 and 2 will cancel. Minus and minus will be plus. And so for the next term, del y of this whole thing, x is now to be treated as a constant quantity. X comes out. And so you have got x squared plus y squared square rooted 1 upon square root of that thing, or rather x squared plus y squared raised to minus half. So that shall be minus half x squared plus y squared raised to minus 3 half. Then you go inside the bracket and that will be, take the derivative of y squared, that will be 2y. Again, the 2's will cancel and you'll just have minus. So 1 minus here and 2 minuses here. Minus into minus is plus. So basically, you have a common term, x squared plus y squared raised to minus 3 half. So minus into minus is plus xy. Minus into xy will be minus xy. You have these two things cancelling out. And you have got a 0 scalar. That is the feature of a solenoidal vector field. The field lines close upon themselves. So closed loop field line will give you 0 divergence. I shall now go into discussing some ideas in greater detail in a supplementary set of notes. We have come to the end of this set of notes on discussing the physical implication of the divergence operator, but I shall look into these things in some greater detail now. So I'll just stop here and begin a new presentation. Please just bear with me. I shall start the presentation. Can you please confirm that you can see the presentation?
Yes.
Hello?
Sir, you can see.
Okay.
Yes.
Thank you. Please mute your mic, or you have confirmed it. Thank you. So this is something that we discussed in the last class, differential equations and all that. There's an error over here. F is equal to minus gm1 m2 by r squared. Right, this is the law of it. So the square is missing. I'll correct that in the notes and give it to you later. We also talked about derivatives and differential operators, and I may mention to you just something that we took up a while ago, f as a function of x, and that's the slope when you talk about multiple variables. This is the variation of the function. These are things we talked about. Now we shall begin this new discussion with some basic ideas. First of all, commutativity of the vector dot product. When we talked about the del operator, occasionally we have to take a dot of it with a vector. Note that I'm not calling it a dot product when you take del. But when you take two quantities, as in A and B, you have two quantities as in A and B, and so the dot product is A dot B, which is also equal to B dot A. It doesn't matter because ultimately you'll just be taking the scalar magnitude. So A dot B and B dot A will give you the same thing, and that is AB cos theta. What about now, instead of A dot B, what about if you have something like del dot A? Vector quantities and vector operators. Let us see. A and B, AX x cap plus AY y cap plus AZ z cap, and similarly for B, these are vector quantities, right? But del is not a quantity. It is a vector differential operator. By itself, it means nothing. X cap del del x plus y cap del del y, z cap del del z. You'll say, okay, fine, so what? I mean, it's just an operator. It's unless it is operating on something, it conveys no meaning. So del is the vector differential operator. As a result of that, although here you can say A dot B is equal to B dot A, when you're taking two vector quantities and applying the dot rule between them, you've got A dot B is equal to B dot A. This is permissible under the commutativity law principle, that thing. But you can't do that in the case of the vector differential operator. You can write del dot A, that is fine, but you can't write A dot L. I'm sorry, A dot del. A dot del is not permitted. Something must follow the del. It has to operate on a scalar or something to give you some meanings. So be very careful about that. A dot B is equal to B dot A, fine, but del dot A is not the same thing as A dot del. It's not, I shouldn't even be writing not equal to it. The right hand side is meaningless. When you can write equal to or not equal to, that is also between quantities, but the right hand side is not even a quantity. So, but for want of any other better term, I've written not equal to. Okay, certain cases of divergence, source and sink. Here you have, this is a black point. Things are coming out of that. Divergence will be positive, so from a source. Things are going into this, divergence is negative. Things are sinking into this, and so you call this point a sink. But when you have neither divergence as in the first diagram, nor convergence as in the second diagram, then you'll have divergence of A is equal to 0. Just a while ago, we worked on an example of a vector with two components, x and y, circular vector field, and there we saw that its divergence was coming out to be 0, neither source nor sink. Just a few other basic concepts to talk about. In the cross product rule, I mentioned in the previous set of notes how to take the cross product. You have got two vectors. You see that this is the rule. X cap is along the x direction, y cap is along the y direction, z cap is to the right, I'm sorry, and z cap is perpendicular. So all three vectors are perpendicular to one another. So when you say x cap cross y cap, they're all unit vectors. X cap, the first vector swept onto the second vector, will give you the third vector. 1 cross 2 is equal to 3. X cap is 1, y cap is 2, z cap is 3. 1 cross 2 is equal to 3. Okay. Next is that you bring the 2 to the position of 1, 3 to the position of 2, and then in a cyclical order, x will go to the 1 will go to the previous third position. And then again, you bring 3 to the position, or 2 to the position of 1, or z to the position, first position, x to the second position, and like this, you'll go this way. So you can see 1, 2, 3, 2, 3, 1, 3, 1, 2. In a cycle, it'll go round. So if you just remember this structure, all of these cross product business, later, right now we are doing Cartesian coordinates, but later we shall do the cylindrical set of coordinates s, phi, z, or we shall do the spherical polar set of coordinates r, theta, phi. So all you have to do is you have to see where you have 1, which coordinate is 1, which coordinate is 2, and which coordinate is 3. And thereafter, you just keep applying everything as I have written down in this table. 1, 2, 3, 2, 3, 1, 3, 1, 2. Just, I mean, if you write the first thing, everything else will follow. And the first thing is not difficult to understand. 1, 2, and 3, three numbers in their regular sequence. 1 cross 2 gives you 3, as in this thing. So these are not numbers. These are symbols standing. First coordinate, 1 meaning first coordinate, 2 meaning second coordinate, 3 meaning third coordinate. Don't think of it as a multiplication. 1 into 2 is 2. That's not equal to 3. This is mathematically, this is an outrage. I mean, arithmetically, this is an outrage. 2 into 3 is 6. It's not like that. So it's not that. It's just a symbolic representation. So there you have this thing. Okay, there is something I would like to now add to our understanding discussed for the gradient operator, namely that of surface normal. Today we have a tutorial. We shall discuss a problem of this type. Let us try to understand the surface normal for a gradient operator. Let us see. What do I mean by this? Suppose you have been given a function phi, which depends on 3 coordinates, x, y, z, and you have been told that the function phi is a constant. Function phi is a constant, but it depends on 3 coordinates. Example, very easy, equation of a sphere. I hope you are aware of what the equation of a sphere is. Equation of a circle is x squared plus y squared is equal to a squared, where a is the radius of a circle. You add a third coordinate, x squared plus y squared plus z squared, and you'll get the equation of a sphere. Circle upgraded to 3 dimension gives you a sphere. Okay, so phi x, y, z, constant radius. So phi x, y, z is x squared plus y squared plus z squared is equal to a squared. So it fits this definition. Phi is equal to a constant. Okay, follow carefully, very carefully. This idea will be important for you later. D phi. If phi is a constant, overall. So you say, how do you mean it depends on 3 functions? How can it be a constant overall? I say it's a very simple thing. If x increases, y and z will decrease to compensate for the increase in x. Something like that will happen. If something increases, one of the coordinates over here will increase. I mean, if some coordinates increase, others will have to decrease to maintain a constancy. That is how it goes. So overall phi is going to be a constant quantity. If phi is a constant quantity, then phi is not changing overall. Therefore, d phi, change of phi is equal to 0. No change. D phi is equal to 0. But then d phi is also gradient of phi dot dl. Gradient of phi dot dl is equal to 0. Okay, now you follow very carefully. This is the surface. Any surface. I've just given you a circle as a very simple example to illustrate the point, but it can be any surface. Phi x, y, z is equal to a constant surface. Right. I mean, it can be a paraboloid or ellipsoid or whatever. And I mean, any kind of surface, provided that overall phi should be a constant quantity. So here's one such surface. Now I've written something over here. Let us try to understand. Moving along the surface from P to Q, dl is a small displacement vector. Now you will say, why should we just be moving along the surface? Along, I have underlined it twice to stress the importance of the word along, preposition. Why just along the surface from P to Q? Why should you just stick to the surface? You have to stick to the surface because phi is a constant. This surface over here, this surface represents the equation of phi. And along that surface, phi is a constant. So if you are, let's say you are occupying some point on this thing, you have to respect this condition that phi is a constant. So if phi is a constant, then you are constrained to move on the surface all the time. You can't go away from the surface, because if you go away from the surface, then you go to a new surface. That's a different value of phi. No. For instance, let us consider this simple example. Not really. X squared plus y squared plus z squared is equal to 1. What is 1? A squared is equal to 1, meaning A is equal to 1. That is a sphere of radius 1 unit. Suppose I give you a function x squared plus y squared plus z squared is equal to 4. A squared is equal to 4. That is, A is equal to 2. That is a sphere of radius 2 unit. So A is equal to 1, you will be on a sphere of radius 1 unit. A is equal to 2, you are on a sphere of radius 2 units, like that. But you are not allowed to change the value of A. A must be constant. Therefore, if you are, I'm saying that you are on the surface of a sphere of radius 1, you must always be on the surface, that surface. You can't go up to a sphere with a larger radius. So that is what it is. You're always constrained to move along the surface from P to Q. And what is P to Q is a small displacement from P to Q. And so the displacement between P to Q is dl. Okay. If dl is along the surface, follow carefully, dl is along the surface, overall d phi is equal to 0. D phi is equal to 0 because you are constrained to be on the surface. dl is along the surface, and dl is not equal to 0. dl is not equal to 0. So dl is not equal to 0. D phi is equal to 0. And gradient of phi, of course, can't be 0. You can just check for yourselves. You take the gradient of phi of this quantity, what will you get? You will get 2x x cap plus 2y y cap plus 2z z cap. Just apply the del operator on this phi, and you will get 2x x cap del del x of this quantity, phi. X cap del del x of phi will give you 2x x cap. Similarly, y cap del del y of this thing will give you 2y y cap. And likewise, del del z of z, this whole phi will give you 2z z cap. So del phi is not equal to 0. Del phi is not equal to 0. dl is not equal to 0. But the fact that the surface is a constant surface means d phi is equal to 0. So the dot product of these two things will be equal to 0. But individually, their magnitudes are not 0. Then it just means only one thing. Del phi, if dl is along the surface, tangential to the surface, del phi must be perpendicular to dl. And if dl is tangential to the surface, as I'm saying, then del phi, what is the perpendicular to a tangent? Normal. Del phi is normal to a surface. Scalar function given by phi xyz is equal to a constant quantity c. So always remember, this is just a general discussion I have held, although I have given you a specific example of x squared plus y squared of a sphere, but here in this discussion, we did not involve any particular equation. This can apply to any kind of a surface, and I have not drawn a sphere here. It's just a section of any surface which is obeying this condition that phi is equal to constant. As soon as you see phi is equal to constant, remember, del of phi will always be perpendicular to the surface. dl is along the surface, del phi will be perpendicular to the surface. Del phi is perpendicular to dl, that is to say del phi is normal to a surface, normal as in perpendicular. Okay, let us see what happens when the surface is increased. That is to say, just a while ago I gave you the example. You go from a sphere of radius 1 to a sphere of radius 2. Here we are. Gradient operator, increase of the surface. I've given you the equation of a sphere as a simple example to illustrate the point. A is the radius of the sphere. On the surface of the sphere, phi is fixed. Phi is equal to a squared. Phi xyz is equal to a squared. As a is the same everywhere, radius of a sphere is the same everywhere. Now I'm saying now you have to increase the surface. Now, if you have to increase the surface, now you cannot move along the surface, because if you just move along, the equation of the surface is phi is equal to a squared. So if you keep moving all over the surface, then a is not changing. If a is not changing, phi is not changing. So you have to increase the surface. To increase the surface, you cannot move along the surface only. You have to move away from the surface. And so it is. Here we are. Z, x, y, z. This is a sphere of radius, some radius. This is another sphere of some other radius. The surface can only be increased by moving along the radius of the sphere, that is normal to the closed surface, positive outwards. So del phi, as you can see, del phi is perpendicular to the spherical surface, right? I'm just discussing it with the example of a spherical surface, but be it understood, the principle shall apply to other surfaces as well, right? is just, let's say I'm asking you to blow out a balloon. Blow into a balloon and fill it with air. You can't, if you have to blow a balloon out, you'll have to make the balloon increase in its radius. You can't just be like an ant, move all over the balloon and hope that the surface is increasing. No, that is not what is going to happen. So del phi will point along the increasing direction of phi. Follow very carefully. You follow very carefully this point. What did I tell you earlier in the previous set of notes? What does del phi serve? Del phi tells you the rate of change. Careful. Understand this point carefully, extremely attentively. Del phi gives you the rate of change with respect to the space coordinates x, y, z along the direction in which phi is changing maximally. That is what del phi does. So suppose you are dealing with a sphere and I'm asking you, what is the direction in which the sphere can change its size maximally? Of course, along the radial direction. If the sphere is a balloon, you blow up the balloon, you fill the balloon with air, and the balloon will start increasing all along the radial track, along the radial direction. That is the direction along which the balloon will change its size maximally. What is phi over here? Phi is the size of this sphere. What function does phi represent, physically speaking? Phi is equal to a squared. A changes, phi changes. And what is a? Radius. If the radius changes, the surface will change. And so this spherical surface will change maximally along the radial direction, and it is along the radial direction that del phi is also pointing. That is consistent with the fact. So two things are consistent with each other. First, a spherical surface will change the fastest along the radial direction. Fine. The equation of the spherical surface is given by this function phi, scalar function phi. Fine. And the gradient of phi is going to give the change, rate of change along the maximal direction. Right. And in this case, the gradient of phi is aligned with the radial direction of the increment of this surface. So all these statements are consistent with one another. So basically, as soon as you see this kind of a function, surface normal, phi is equal to constant, two things you have to realize immediately. First, gradient of phi will be normal to the surface, number one. Number two, gradient operator, the gradient operation of phi will also point along the direction, point in the direction along which the surface is going to change at the fastest possible rate. So surface can only be increased by moving along the radius of the sphere. That is normal to the closed surface, positive outwards. That is very important. Gradient of phi will always be pointing outwards. It's a positive function. Radius is a positive quantity. I hope you'll agree with me that nobody has ever talked about a negative radius. As soon as you see this thing, I said a squared. So a is the radius. You say, why didn't I say minus a is the radius? Because if I put minus a over here, that would also have been equal to, a were to have been a negative quantity. If a were to have been a negative quantity, then this thing would have been, the square would still have been a positive quantity. There is no problem with that arithmetically. No, indeed. But physically, there's a serious problem. You can't have a negative radius. Radius is always coming from the origin, 0.0 outwards. If you say negative radius, it is actually like saying that it is going inside the point. But what can go inside a point? So it makes no sense really to talk about a negative radius. So that's why if the radius is positive and del phi is also aligned along the radial direction, then del phi must also be a positive outward normal vector to the closed surface. That is what it is. We can apply this, extend this principle to a physical example with which we are familiar. What is the physical example? Gradient of the atmospheric temperature. Let us see. In one of the previous classes, we discussed this point. Air temperature or air density also, it applies the same way, both same principle applies to both cases, both physical quantities, temperature and density, increases along the vertical direction, that is the z-axis. There is no change along the surface of the Earth, that is along the x and y axis. If the distance is small to approximate a flat Earth surface, what do I mean by this thing? It's a bit of an overkill, really. I mean, of course, if I say that you walk along the surface of the Earth 10 kilometers from this south of Gandhinagar city where DICT is located, I think you all joined in the year 2020, so you have not been able to come to the campus. Right, even for once probably. So Gandhinagar's DICT campus is located to the south of Gandhinagar city. So if I ask you to go 10 kilometers northwards, so you just take the Ghar road track and go all the way past the secretariat and all that and go all the way to the end of the city, you would have traveled 10 kilometers. Or you can take 10 kilometers, so that will be northwards. You can take 10 kilometers in an easterly direction. So you'll go across the Sabarmati River, you'll go past the IIT campus to the next district on the other side of the river. No, sorry, on the other side, what's the district? I don't know. So whatever. So 10 kilometers, you'll be actually on the border of Gandhinagar district. But either way, whether you go 10 kilometers north or 10 kilometers east along the ground, you will not feel any change of temperature. You'll be as comfortable or because of the coolness of the air, or as uncomfortable because of the heat and the humidity within this 10-kilometer range. But if you go 10 kilometers vertically upwards, you'll actually would have gone to a height that is higher than that of Mount Everest, which is the tallest mountain on the surface of the Earth. Mount Everest is slightly below 9 kilometers in height. So you'd have gone. So you will immediately be able to sense the change of temperature. It will be freezing cold, 10 kilometers above the surface of the Earth. So air temperature increases only along the vertical direction, that is the z-axis. So there is no change along the surface of the Earth, that is along the x and y axis, if the distance is small to approximate a flat Earth surface. So if you travel 10 kilometers, you can treat the Earth as flat. But if you have to travel from the equator to the North Pole, the Earth is not flat. And incidentally, on the surface of the Earth, you'll know that it can get very cold. And the North Pole is on the surface of the Earth, but it's very cold over there. But that's a different kind of geometry now. It's not a flat Earth geometry. I'm just talking about Cartesian geometry where x, y, z, and all the planes, x, y, y, z, zx. What do I mean by that? Here it is. There's the diagram. So here it is. This plane is xy plane. This plane is yz plane. This plane is zx plane. So all the surfaces are to be treated as constants. So here you are, if x is pointing in the north direction, then y should point in the west direction and z is vertically upward. So you're assuming a flat earth kind of a scenario. So if you travel a small distance, 10 kilometers is satisfactorily small compared to the radius of the earth and all that. So you can still experience something like a flat earth, but the earth is not really flat. So if you were to take the gradient of the atmospheric temperature, if temperature is a scalar function, and the height of the earth is serving as A. So at a particular height, let's say phi is equal to x, y, z, and at a particular height, if you fix the height, temperature will be the same everywhere. That's not changing. But if you have to move from one height to another height, the temperature will change. So if phi is like your temperature. So what is the axis along which the temperature is changing maximally? Z-axis. Here, what is the direction or axis, if you like, along which phi is changing maximally? Phi as in the surface of a sphere, along the radial direction. You can say the radius can serve as the axis also. Whatever. So that is the general idea of this discussion. I'll just briefly touch upon this issue of the extremal condition of the gradient, so that here it is. In 1D, f is equal to fx. The maximum or minimum of f is given by df dx is equal to 0. Remember, first derivative is equal to 0 is known as the extremum condition. It can capture both a maximum or a minimum. How will you distinguish between the two? You look at the second derivative, which I have not discussed over here, but I expect you to know. The second derivative, this is something that we learn in school calculus. Second derivative is positive, meaning it's a stable minimum. Second derivative is negative, meaning it is an unstable maximum. So that is what you have, the extremal condition for in 1D. In 3D, instead of f depending on x, you have phi is depending on x, y, z. And the extremum condition will be gradient of phi is equal to 0. Not df dx is equal to 0, but gradient of phi is equal to 0, which when broken down term by term will actually be like this. Dx is equal to 0, but except that you'll have three things: del phi del x, del phi del y, and del phi del z. Each of them will be equal to 0. So that is what it means, because three vector things, mutually perpendicular components, adding up to 0 means that each one of them will be individually 0. Otherwise, I mean, the x, whatever is happening along the x cap direction can't affect anything along the y cap, and similarly along the z cap. Therefore, x cap and y cap are not cancelling each other out, and so it is with z cap. Therefore, it means that individually all of them are equal to 0. You can extend this principle to n variables, where phi is a function of n coordinates. Instead of just x, y, z, you can write x1, x2, x3 up to xn in n-dimensional space. So in that case, in n-dimensional space, the extremization of n variables will just be an extension of this 3D case to this n-dimensional case. Del phi del x1 is equal to del phi del x2 is equal to etc. going up to del phi del xn is equal to 0. Let us look at this discussion of this divergence operation that we just discussed a while ago. I mentioned this thing to you. G is equal to minus y square root of x squared plus y squared x cap plus x divided by square root of x squared plus y squared y cap. Divergence of G is equal to 0. That we have seen. If you take the divergence of this thing, it will be equal to 0. Let us understand this thing geometrically a little. This thing is known as a solenoidal function. I have to touch upon that word solenoidal in greater detail now. Let us see now. We discussed that this function has got a radius, this vector has got a radius of 1. At this point A, x is equal to 1, y is equal to 0. At this point B, here, x is equal to 0, y is equal to 1. You put this thing when y is equal to 0 as here and x is equal to 1, g is equal to y cap. At A, g will point upwards this way. Y cap plus y cap. When x is equal to 0 and y is equal to 1, put this thing over here, g will be equal to minus x cap. At B0, 1, g points to the left, minus this thing. So these things are tangential. Right, tangentially, the tangent to a curve gives the direction at that point instantaneously, instantaneous direction. This kind of a vector field is known as a solenoidal vector field. Just try to imagine, I have drawn the x-axis in the right direction, the y-axis in the vertical direction. There is a z-axis. The z-axis can't be drawn, it's a third axis drawn on a plane. The z-axis is pointing towards you. If you're looking at this figure, the z-axis is right now traveling towards you, drilling right into your eyes. Z-axis is pointing towards you, you can do something. Take your right hand, point the thumb towards your eyes, and curl the fingers around the direction of the thumb. Take your right hand, point the thumb towards your eyes, and curl the fingers. So the thumb is along the z-axis, it is pointing towards you, and the fingers are curling like that. What does that remind you of? Ampere's right-hand rule. If the thumb is pointing at the direction of the current, then circling all along that axis will be magnetic field lines. like a solenoid. A solenoid goes like this. So it's a solenoidal field. A solenoidal field shows zero divergence, and you can immediately see magnetic field lines, if they are to behave like this, Z is pointing towards your eyes. You align the thumb along the Z direction and point the thumb towards your face. And make the fingers curl around your thumb like this. The fingers of your right hand will be curling along the magnetic field lines, and the divergence of those field lines will be equal to zero. For a straight wire conductor, if a current is flowing along that straight wire conductor, the magnetic field lines are going to be like this, and they will show zero divergence. So that's something that I have mentioned, going a little ahead of the story, but I think you should basically now try to see what it is like. If we go back to this diagram here, these will be the field lines of a positive charge. These will be the field lines of a negative charge, or for that matter, even gravity, the gravity of the Earth, let us say. And these will be the field lines of a magnetic. This black dot is not a black dot. The black dot is a straight wire that you are looking at head on. If you look at a straight line head on, you will see a point. But this is not a point. This is actually a straight line looked up at head on. But this is a point. This is a point. But this is not a point. This is an axis. You're looking at the axis head on. That's why you're seeing a point. And from your perspective, you'll see field lines circling like that. If a current is flowing along the axis towards you, then by Ampere's right-hand rule, you'll see. So you can see immediately electrostatic field lines will obey these conditions depending on the plus or the minus nature of the charge, and magnetic field lines will obey this condition. Divergence of magnetic field lines will be equal to zero. Okay, but that will come to in greater detail later. Certain features of partial derivatives we shall touch upon before we go on to our next discussion. These are the features. A very important thing, arithmetically speaking, let us try to see. In Cartesian coordinate, you have a general vector field, ax, x cap, ay, y cap, az, z cap, where in the most general sense, each of these magnitudes, ax, ay, az, can depend on all the three coordinates x, y, z. In general, depend on all the three coordinates x, y, z. It's important for you to realize this thing, because it doesn't mean that the x component depends only on x. No. Or the y component depends only on y, or similarly for z. No. The x component, the magnitude part of the x component can depend on the other two coordinates as well, y and z, namely y and z. Okay, now you consider a scalar function. Psi is equal to psi xy. Okay, del psi del x is in general not equal to del psi del y. But important property of second derivative, mixed second derivatives. First I take del psi del x, then I take del y of that. And on the right hand side, first I take del psi del y, then I take the second derivative with respect to x. The first derivatives with two different coordinates need not be equal to each other. They can be, but they need not be in the most general sense. But mathematically, in the most general sense, second order mixed derivatives are the same. Not first derivative, but second order mixed derivatives. And not pure derivatives. For instance, del 2 psi del x squared need not be equal to del 2 psi del y squared. But if you are mixing the derivatives, first with respect to x, then with respect to y, or first with respect to y, then with respect to x, then they are going to be equal to each other. Del 2 psi del y del x is equal to del 2 psi del x del y. Mixed second derivatives are the same. We'll just look upon an example over here. Psi is equal to x squared plus y squared plus z squared. Del psi del x is equal to 2x. That is independent of y and z. Okay, and so del psi del y will similarly be equal to 2y. You can now immediately take the mixed second derivative. Del 2 psi del y del x will be equal to 0, and similarly for del 2 psi del x del y will be equal to 0. There is a third thing. Don't be under this misapprehension that if you take a derivative with respect to psi, with respect to a particular coordinate x, the derivative will depend only on x. No, the derivative can depend on other coordinates as well. For instance, psi is equal to x, y, z. When I take the derivative with respect to x, del psi del y, x is equal to y, z, depend on y and z. So in general, partial derivatives with respect to one variable a, say x, may depend on the other variables y or z. So these are mathematical generalizations which we shall use. So for a vector field, as I have mentioned, ax this thing, all ax, ay, az and their derivatives of any order and their derivatives of any order can in general depend on x, y, z. I shall stop the sharing of this thing. We have 10 minutes left. Today we shall no longer take those extra 5 minutes as I did to compensate for the mistaken loss of 15 minutes in the first lecture. Today we shall finish at 11:30 sharp. So there are now 9 minutes left. In the 9 minutes, I shall now start beginning to discuss the physical meaning of the curl operators. So far we have discussed the physical interpretation of the gradient operator in various ways and the divergence operator. So now with the understanding of the features of partial derivatives as we have discussed over here, we shall begin our discussion of the curl operator. So I shall stop the sharing and I shall begin a new set of slides. Please bear with me. Um, Please confirm that you can see the presentation, one of you, please. Thank you.
Yes, sir.
Yes.
Okay. Thank you. Thank you. So we shall take up the curl operator now. So instead of getting into too much mathematical detail, I shall begin with a simple example, namely that of a central force field. What is a central force field? A central force field is one in which the force depends on the radial vector only and is directed only along the radial vector. So basically, you will have f as a function only of the radial vector r, the magnitude part, and the vector part will just be r cap. So consider f r cap as an example of a general central field. So as you can see, if the field lines are going outwards, you will have fr being equal to positive. If the field lines are going inwards, Fr is negative. This is a repulsive field, as in the case of, let's say, a positive charge. This is an attractive field, as in the case of gravity. Most familiar example, as in gravity, what is the gravitational field? F is equal to minus gm by r squared. It is an acceleration field, actually, because when you multiply this thing with a mass into acceleration, overall will give you a force. So as in gravity. So F is an acceleration field. So that is a central field. Let us just briefly discuss the nature of this central field. As you can see, I'm plotting Fr along the vertical axis and R along the horizontal axis. From D to C, I have proceeded. So I have got Fr will always be negative because it's falling below the minus. So if it is negative, it will always be below this horizontal axis. Fr will have a negative value. R will have a positive value all the time. Remember, our radius is always positive. So you have moved a certain step size from D to C. So as you have moved from D is this position, to C, your field has changed by this little gap, C prime and D prime. And as you have moved from B to A, you moved from D to C, this is your shift. Your field has changed by the distance or by a spacing of C prime, D prime to C prime. But as you move from B to A you have moved, your field has changed from B prime to A prime. So you can see this is a much smaller gap compared to this gap. D prime to C prime is much smaller compared to B prime to A prime.
Why is that happening? It is happening because of this inverse square nature of the force. It's not a linear behavior. So that is what it is. In electrostatics, Fr is equal to Q by 4 pi epsilon naught R squared. Whether Fr will be positive or negative will entirely depend on the sign of Q. If Q is a negative sign, then Q has a negative sign, then electrostatics field will be like this. If Q has got a positive sign, a positive charge, the electrostatic field lines will be like this. So now let us look at the radial vector. Vector R is equal to x cap plus y cap plus z cap is equal to R into R cap. I hope you have no difficulty understanding this. This is the most general way in which you can write the radial vector in terms of decomposing it into its Cartesian components. Okay, let us look at this R cap unit vector. R cap therefore is equal to x by R, x cap, y by R, y cap, z by R, z cap. Just dividing this equation throughout by R. That is all that I've done. And what about R itself? Magnitude of R. Magnitude of R is equal to x squared plus y squared plus z squared raised to half. That's the equation of a sphere actually of radius R. Okay, so f of R cap, is f of R multiplied by R cap is now I'm writing it like x by R, x cap, y by R, y cap, z by R, z cap. Taking R as a common factor, I'm writing taking it outside. So define phi R. So you can see that this thing is just a function of R. F of R is a function of R, which we do not know. It can be anything. And in the denominator, you have another R. So I'm writing this whole package together as phi of R. If R is a general function, so it doesn't have to be gravity or electrostatics or anything. It can be anything else, except that only thing is that it just depends on R, nothing else. Okay, f of R cap could now be written as phi of R into x cap plus y cap plus z cap. Okay, our next task will be to take the curl of f. Curl of f, R cap. What is that going to be? Let's see, x cap, y cap, z cap. I hope you have not forgotten what we should write when we take the curl. Next thing is del x, del y, del z in the determinant. We discussed it in the previous class. And now what about the x component of fr? Phi into x. Remember, phi depends on r and r depends on x. Therefore, you can't ignore this thing. So phi into x plus phi into y plus phi into z, where phi depends on all three coordinates x, y, z, and because phi depends on r, the radius vector, and the radial vector depends on the three coordinates x, y, z. So implicitly, phi depends on x, y, z. So basically, you shall just have to take the determinant of this thing. Now, I hope you know how to take a determinant. X cap is equal to del y of phi z minus del z of phi y minus y cap del x of phi z minus del z of phi x. So del x of phi z minus del z of phi x. And then z cap del x of phi y minus del y of phi x. So there you have these three things. Next task, very careful. Don't treat the phi as a constant because phi depends on r. No, sir. Phi depends on x, y, z because as phi depends on r, it must also depend on x, y, z. Therefore, phi is not a constant with respect to y. So you have to apply the chain rule. What is it? Let's see now. Z as a constant. Z can come out because you're taking the derivative with respect to y. Remember, x, y, z are independent of one another. So I'm taking the z out. So z, then you will have, I'm taking this thing z del phi del y. I'm writing as z del phi del r and del r del y. Then this thing will be y del phi del z will be y del phi del r into del r del z. Similarly, here you will have z del phi del r into del r del x, and here you will have x del phi del r into del r del z, and here you will have y del phi del r del x, and likewise the last term shall be x del phi del r del y. Last thing Here it's a very simple thing. R squared is equal to x squared plus y squared plus z squared. Take the derivative of this thing. 2r del x is equal to 2x. When I take the partial derivative with respect to x, y, and z are constants. So del x is equal to x by r. And similarly, by the same principle, you can immediately conclude that del y will be equal to y by r, and del z will be equal to z by r. You can just see this thing is done over here. So curl of fr, just give me a minute, I shall finish in a minute. Curl of f, this whole thing written like this thing will now be equal to del y will be y by r, del z will be z by r. Del phi del r is a common factor in all the three terms. Del phi del r is a common factor. Therefore, we can pull out the del phi del r out of every single bracket. And here you will have z y by r minus y z by r. And they will cancel. Z y by r minus y z by r. Similarly, in the second term, you will have z x by r minus x z by r. They will also cancel. And in the last term, you will have y x by r minus x y by r. So they will also cancel. So identically, curl of fr is going to cancel, and you'll have a zero vector, 0x cap minus 0y cap plus 0z cap is a zero vector. So curl of fr r cap is equal to vector 0 as it happens. In the case of an electrostatic field line, this is known as an irrotational vector field. Field lines are centrally directed inwards or outwards. Irrotational meaning, that's the last point I'm taking up. Irrotational as in these lines are just going right straight out or straight in. They are not rotating or going round and round. So that's why it's an irrotational. Anyway, I shall stop here. We have finished the discussion for the day. We have a tutorial at 2. We shall meet at 2. I shall send you the link for the tutorial and the tutorial problem sheet as well. If you want to raise any question or anything, you can ask me now. Otherwise, we can. I'll anyway stop the recording. Nobody has a question?